Data serialization we had seen in some earlier portions. So when we talked about rotation, uh, RRC, RAL, RLC, etc. So in that we had dealt with data serialization. That is, by rotating, you are sending out the bit starting from LSB or starting from MSB to a particular port, say port bit. So serially you're transmitting the data bit by bit to a port from the accumulator. So this we have already dealt with. So next, let's see how do we do the same using a C program. So there we had dealt with it in assembly language program. So here we are dealing with C program. So in C program, the question is send out the value 44H serially 1 bit at a time via P10. LSB should go first. So if you are writing the assembly language program, then we'll move 44H to accumulator first, then rotate to the right because LSB should go first. Rotate to the right with carry 2, and the carry value that will be sent to the port, whichever port here P10. So that is the basic logic which we will be using in the case of assembly language programming. So when you're writing C programming, so it is bit by bit. So P10 should be declared first. It's a single bit. So this is just the name given to that. And accumulator also you want to transmit the accumulator LSB. LSB you are going to transmit to P10. So we are not making use of the carry concept here. So accumulator LSB that will be sent to P10 directly. So ACC0, this is the LSB of accumulator that will be sent to P10. So register LSB will be moved to P1B0. That is what you are going to do. So by rotating to the right. So we have defined the accumulator LSB and P10, and then we'll just declare a particular character, and you're going to move 44H to this particular variable con byte. So since this is only 44H and you can use unsigned character up to FF, I'm using unsigned character here. So these are just names. You can give any name, no problem. So I've moved 44H to this particular variable and a counter is set. So accumulator, we know it is 8 bits long. So 0 to x less than 8. X less than 8 means 7. So 0 to 7 means 8 bits. So accumulator 0, 0th bit to 7th bit. So you're incrementing x from 0 to 7 and moving the register ALSB, that is the accumulator content. Which accumulator content? The LSB of the accumulator to where? P10. So the first bit goes to P10, then you're shifting it to the right, and this will continue for all the 8 bits. So logic is the same, only difference is that in the case of in the earlier case when we did the assembly language programming, we rotated through the carry because the carry only can be transferred to the P10, but here we are able to transfer this directly. So we are not using any carry. So that is shifting to the right and serially transferring the data. So again, if it is MSB that you want to transfer, then shift to the left. And another difference will be, we'll be shifting out each time the D7 bit or the accumulator 7 bit to P10. So that's why we have written here accumulator 7, and here we have moved accumulator 7 or the MSB of the accumulator to P10 and shift to the left. You can see the arrow direction. Write a C program to bring in a byte of data serially 1 bit at a time via P10. LSB should come in first. Bring in a byte of data serially 1 bit at a time via P10. So you want to fill the accumulator with the data 8 bits, 1 bit at a time, and P10 will have the data which should be transferred to the accumulator. So it's the other way around. In the earlier two cases, you are moving the accumulator contents out to the P10. In this case, we are getting the data from P10 and moving it into the accumulator. So only the direction of transfer of data that will change. So P10 again and accumulator we've defined, and X is again 8 bits, and this is the input. So P10 is the input, and the accumulator will shift to the right by 1 bit. So why are we shifting it to the right? Because the LSB comes first. So the LSB should move to the LSB position. So here you're taking in the bit at the MSB, and from MSB you're going to shift it by 8 positions so that it goes to the LSB position. And after shifting in all the data, then you're going to transfer the data from the accumulator to P2. So you'll be storing the data in P2. Here MSB should come first. So MSB should come first means you'll be transferring it from right to left. So left shift. So you'll be entering it through the LSB. That's why here you have the accumulator 0 and shift to the left. Serial communication in 8051. So we know that in computer, the transfer of data is in two ways. One is parallel and one is serial. So here we will be looking at serial communication. So to transfer to a device located at a distance, the serial communication is used. So what do you mean by serial communication? It is 1 bit at a time. Okay, bit by bit the data will be transferred. So that is serial communication. So if you have a sender or a transmitter and a receiver at two different places, then the sender will transmit the data to the receiver bit by bit in the case of serial transfer. So the first case we see here is serial transfer. You have just one line, and in that line, one bit at a time will be transferred to the receiver. Whereas in the parallel transfer, all the bits will be transferred through multiple lines at the same time. So we are focusing only on serial communication here. So at the transmitting end, if we are if you have bytes of data, okay, so these bytes of data, if you are going to transfer through serial communication mode, then you have to convert this particular byte into bits and then transmit it one bit at a time. So for that, it should be converted to serial bits using the parallel in serial out shift register. We have studied PISO shift register in LCD, logic circuit design, or in digital electronics. So in that we discussed about how the parallel serial out shift register works. So the input will be given in parallel, that is in this case say a byte of data. So that byte of data, that is 8 bits of data, will be taken in by the shift register in parallel, and then it will be shifted out in the serial fashion one bit at a time. And at the receiving end, you have the serial in parallel out. Okay, so it will be receiving in the serial fashion because SIPO is the shift register at the transmitter end, and you will have PISO is the shift register in the transmitting end, and you have the reverse, that is SIPO shift register in the receiving end. So it is parallel in serial out at the transmitting end and serial in parallel out in the receiving end. So if the distance is very small, then you can just transmit it through a simple wire, and if it's at a distance, very long distance, then you can transfer it through telephone lines. So if you are using the telephone lines, then from zeros and ones, it should be converted to audio tones. So that can be done using a modem or the modulator, demodulator. So the serial communication uses two methods. One is the synchronous and the other is the asynchronous. So we know what synchronous is and what asynchronous is. So in synchronous, it transfers a block of data at a time, and in asynchronous, it transfers a single byte at a time. Okay, so it is serial, it will be transmitted bit by bit only, but then even bit by bit, whether it is transmitting one byte at a time or many bytes or blocks of data at a time, that will decide on whether we are using synchronous or asynchronous method in serial communication. So what is the difference between serial and parallel communication? How do we transmit the data from the transmitter to the receiver with the help of shift registers, and what are the two types of serial communication, and what is a modem, why is the modem used? So instead of writing a software to use the synchronous or asynchronous method, because the programs will be quite long, so instead of that, we use normally hardwares or the IC chips, and those chips used for serial communication are called UART and USART. UART is the universal asynchronous receiver transmitter, and USART is the universal synchronous asynchronous receiver transmitter. So you have the UART and the USART. Those are IC chips to enable serial communication, so that you needn't write long programs to do the serial communication. Now we talked about two types of serial communication, synchronous and asynchronous. Next is how is the data transmitted and received. So data can be transmitted and received either using a half duplex or a full duplex. In general, it's called a duplex transmission. That is, serial communication makes use of duplex transmission method to transmit the data bit by bit between the transmitter and the receiver. So what is half duplex? Half duplex means the data can be transmitted only from the in one way. Okay, and full duplex means it can be transmitted in both the ways. It is if the transmitted if it's transmitted one way at a time, it is called half duplex, and if the data can go both ways at a time, it is called full duplex. So here you can see that in full duplex you have two lines. So the transmitter can transmit to the receiver, and also from here it can transmit to the receiver. So you have two lines, so that it is called a full duplex. And in the case of half duplex, the transmitter can transmit to, or this transmitter can transmit. That will depend on the switch in the middle. Okay. So the last method, that is the full duplex method, that is controlled using a switch. This transmission is controlled using the switch in the case of half duplex. So at a time, it can transmit only one way. It can transmit in two ways, but not at the same time. But in full duplex, it can transmit in either ways at the same time. Simplex is there is only one way of transmission. You cannot transmit the other way. Okay, so normally we make use of half duplex and full duplex in serial communication. Then next term you should know is a protocol. A protocol is a set of rules between the sender and the receiver, or the transmitter and the receiver, depending on how the data is packed, because the transmitter transmits the data to the receiver. Now the receiver should know how the transmitter will pack the data. Only then the receiver will understand what is the data that has been sent to the receiver, like what has been received. Okay, so suppose there are parity bits, so the or stop bit, start bit. So in addition to the data, there are other bits also packed into the transmitted data. Okay, so suppose you have 1 byte long of data sent one bit at a time. So instead of 8 bits, the receiver gets say 10 bits. So the receiver should know what are these 10 bits, which is the bit that is coming in first. Is it the LSB? Is it the MSB? Is it some other bit? And what does that bit signify? All these things the receiver should know. Only then will it understand what the transmitter actually sent it, because ultimately everything is just zeros and ones. Okay, so by receiving a series of zeros and ones, the receiver should understand which one means what, which zero means what. So for that, they should have a set of rules or protocol. So how the data is packed, how many bits constitute a character, and when the data begins and ends. So from here to here is the data. Rest of the bits are something else. And what are those extra bits? So all these details the receiver and transmitter should comply to. Okay, the transmitter cannot just send the data as it likes, and the receiver will not understand what the transmitter has sent. So they should both have the same set of rules. So for character oriented transmissions, if you are sending characters, then asynchronous serial data communication is mostly used. So each character is placed in between start and stop bits, and this is called framing. So what is a start bit, what is a stop bit, we will see in due course. Just understand that beginning of the character is called the start bit, and after the character ends, you send a stop bit. And if you are transmitting it using block oriented data transfers, if it's not one character at a time, if you are going to transmit blocks of characters at the same time, then it uses synchronous method. So what is a start bit and what is a stop bit? So start bit is always one bit. Okay, so there are communications where the start bit is also, it's not start bit, it's start bits. Okay, there are more than one bit uh, which will indicate the start bit, and there are more than one bits for the stop bits. So in this particular case, we are dealing with only one single start bit and one single stop bit. Sorry, stop bit can be one or two bits. Start bit can be only one bit and stop bit can be one or two bits. That's the case we are dealing with. So the start bit is always a 0 and the stop bits is a 1. So this is how the start and stop bits will look like. So here we are trying to send the character A. So A is the character, ASCII character. So the 8-bit binary equivalent to A is 41H. Okay, so 41H is 01000001. So this is the binary equivalent of the ASCII character A of 41H. Okay. So this particular character you want to transmit, the transmitter needs to transmit from the transmitter to the receiver. So this is the data. So how is it transmitted? You have a start bit here. Okay, so this is the first bit, start bit. Then you have the D0, this one. Then you have the higher order bits. Finally, you have the D7. And after D7, you send the stop bit, saying that the whole character has been sent out. So first we'll start with the start bit. So the first bit will always be taken as the start bit if it is a 0. Okay. Whatever comes after that, the next 8 bits is taken as the data. After that, if it's a 1, then that will be taken as a stop bit. So in this particular case, we are dealing with only one single bit for stop bit. So this is how you transmit serially using the start bit and the stop bit. And if there is a 0, it is called as a space. And when there is no transfer of data, then it is called a mark. And mark is always a 1. And the transmission begins here and in this order. Okay, first start bit, then the 8 bits which you have to, which is the actual data, then the stop bit. So the start bit was a 0. First bit which you transmit is a 0. That is the start bit. Next 8 bits is the actual data. Then you have a 1 which is the stop bit. And the first bit which comes out After the start bit, that will be D0. Then D1, D2, D3 up to D7. After D7, stop bit. And wherever there is a 0, that's called a space. And when there is no data transfer, that's called a mark. And mark is always a 1. So we are dealing with one stop bit in this particular book. So we dealt with 8 bits of data and 2 bits. One is the start bit and the other is the stop bit. So totally you have 10 bits. Okay, that is 2 bit in extra for every character that is sent out. So every character that is sent out will need 2 extra spaces, 2 bit spaces. So that's why they call it as 25% overhead, because 2 by 8. 2 by 8 is 1 by 4, that is 25%. So 25% overhead, that is for each 8-bit character, there is a extra overhead of 2 bits. And there are cases where in addition to the start bit, stop bit and the data bits, you have the parity bits. So why do we need the parity bits? Because suppose there is some during the data transfer there is some error occurring. So in order to find out whether there is any error occurring, you will be inserting a parity bit also to make sure that there is no error. So if there is parity bit in addition, then the overhead will be even more. So we talked about UART. So if you are using UART, then you have parity bit for odd parity, even parity, and even no parity options. Now the data is transferred in serial communication, and the rate of data transfer is called bits per second, and that is also referred to as baud rate. BAUD, baud rate. So if you're dealing with just a conductor wire, then baud rate and BPS is the same. But if you are using modems, then single change of signal transfer several bits of data. It's not one bit at a time. So it will be blocks of data. So RS-232 is an interfacing standard which was set up by EIA, Electronics Industries Association. So it was in RS-232, a 1 or a high is represented from -3 to -25 volt, and 0 is between +3 to +25 volt. So it is the reverse. It is a negative logic sort of thing, because a high is represented by a negative voltage and a low by a positive voltage. So we know what -3 to -25 is, and we know what 0 to +3 is, but we don't know what is between -3 to +3. So that region is undefined in RS-232 standard. So we will skip this. So just a question. If the crystal frequency is 11.0592, find the TH1 value, that is the timer high, timer 1, that higher nibble. value needed to have the following baud rates: 9600, 2400, 1200. So we know that the machine cycle frequency is 11.0592 megahertz divided by 12. 12 is the number of T states. So we know the machine cycle frequency, and this is the setup. If you are using a UART, RS232 is a UART. So if you are using a UART, then you have a divide by 32 at the end. That is, we know for a timer actually crystal oscillator, then divide by 12. Here, from here it was going to the timer. But if you are using a UART, then this will again be divided by 32, and then only the frequency will go to the timer one. So that frequency is 28,800 hertz. So 9600, 2400 and 1200 were the values which you wanted. So you can just divide and see. So the answer will be 3, 12 and 24. So the values which you will be loading to TH1 will be these values: -3, -12 and -24. The negative values will be loaded into TH1. Okay, so this part is the, in syllabus you have SFRs for serial data communication. So that portion is coming up. So SBUF, that is a register for serial communication. So it's an 8-bit register. It is used only for serial communication. Okay, so for a byte data to be transferred via the transmitted line, it must be placed in the SBUF register. So you have the transmitted line, and if you want to send the data through the transmitted line, then it should be placed in the SBUF register. So if you have a byte of data in SBUF, then it will be given the start and stop bits, and the data, the 10 bits will be transferred serially via the transmitted line. So SBUF gets the data when it is received by 8051 received line. So when the bits are received serially via received, the 8051 will deframe it by removing the start and stop bits, and the byte of data is received, and then it will be placed in the SBUF. This is the receiver end. This is the transmitter end. So SBUF, you'll keep the 8-bit data. What happens? It will be framed. How? By giving the start and stop bits to these 8 bits. So the 10 bits have been formed. Using the transmitted line, it will be sent out. In the receiver end, it will be received through the received data, RXD, that line. Then it will be deframed. That is the unnecessary information. That is the start bit, stop bit. All those information will be removed, and only the 8 bits of data will be placed in the SBUF of the receiver. So this is the transmitter side, this is the receiver side. Now how do you do all these? So you have instruction like move SBUF comma hash, this is character, ASCII character D. So SBUF will get the value D. So A we know is 41, B is 42, C is 43 and D is 44. Another method of moving the accumulator contents to SBUF is SBUF comma A. So these are valid instructions which are supported by 8051. And if you want to transfer the data from the SBUF to the accumulator, then you can use this particular instruction. So these are some of the instructions supported by 8051 using SBUF. So SBUF just it is used for serial data transmission and reception. You have one at the transmitter side and the receiver side. In the transmitter side, when SBUF gets the 8 bits, then it will be framed to be with start and stop bits, so that it has a total of 10 bits. It will be transmitted through the transmitted line to the receiver. In the receiver end, it will be received through the received line, deframed, and the data will be transferred to the SBUF of the receiver side. Then you have the SCON register. Again, it's an 8-bit register. It is used to program the start bit, stop bit, and the data bits of data framing, among other things. So these are the bits of SCON. You have SM0 or the SCON 7. Okay, this is just the D7 bit. So that's why you call it SCON 7, D6 bit. So SCON 6, like that. So SM0, SM1, SM2, R enable, TB8, RB8, T1, TI, RI. So we will deal with this later on. So this is you have 2 bits which is not used. So serial port mode specifier. Mode is specified by SM0 and SM1. If you have multiprocessor communication, then you use SM2. To enable or disable the reception of data, you use R enable. Transmit interrupt flag. At the beginning of the stop bit mode 1 and cleared by the SW. RI receive interrupt flag set by SW at the beginning of stop bit mode 1 and cleared by SW. So this will deal with later on. So what is SM0 and SM1? Mode is set using SM0 and SM1. So they determine the framing of data by specifying the number of bits per character and the start and stop bits. So how many bits are there in a character, and the start and stop bit will be specified by the higher order 2 bits. So if it's 0, 0, then it is serial mode. 0, 1, then it is serial mode 1. Data will be 8 bits. 1 start bit and 1 stop bit. 1, 0, serial mode 2. 1, 1, serial mode 3. So 0, 0 is serial mode 0, 1, 0 is serial mode 2, and 1, 1 is serial mode 3. 0, 1 only, it is serial mode 1 and 8 bits of data, 1 stop bit and 1 start bit. So why the others are not talked about? Because we are dealing with only serial mode 1. So serial mode 1 means SM0, SM1 will be 0, 1. So if we are dealing with multiprocessing capability of 8051, then you'll have to use SM2. Receive and enable or R enable. It's a bit addressable register. So when it goes high, when that particular bit is high, it allows the 8051 to receive data on the RxD pin. So at the receiver end, we told that the data will be available at the received data, that pin. So in order to receive that, first this particular signal should be, this particular bit should be made equal to 1. Only then the 8051, the receiver 8051 can receive the data. If it's low, then the receiver is disabled. TI or transmit interrupt. So after a particular transmission is completed, say of 8 bits, then TI will be made equal to 1. So the transmission is complete. So the 8051 should let the transmitter side should uh, inform that the transmission has been completed. It can transmit more data. So in order to inform that, it will make TI equal to 1. So and it is ready to transfer another byte. So when a stop bit comes up, then TI will be made equal to 1. Receive interrupt. So when the 8051 has started to receive the data serially via RxD, it should deframe. That is, it should get rid of start and stop bits and place the 8 bits of data in the SBUF register. So at that time, it will raise the or make Ri equal to 1 to indicate that a byte has been received and should be picked up before it is lost. So Ri equal to 1 means a byte has been received, and this should be picked up and placed in the SBUF before the data goes off. So Ri will be made equal to 1 halfway through the stop bit. So Ti, Ri. Ti is at the transmitter end, Ri is at the receiver end. Ti after transmitting the data, that is when the stop bit comes up, then Ti will be made equal to 1 to let so that the transmitter informs the 8051 that I'm ready to transfer another byte of data. Receive interrupt. After receiving the data, after deframing it, halfway through the stop bit, Ri is made equal to 1. That is, the data has been received, it has been deframed. Now pick up the data before it is lost. So in order to inform this, Ri is made equal to 1. So SBUF, SCON. These are the two registers we talked about in detail.